work, and she's been picked to roll out a wearable version of synthetic telepathy. And I'm going to do my best to illustrate for you that this can be done with microwave technology and current LCD/LED laser type devices that we know as cell phones and tablets. So, tra-la, tra-la.
That's the lady you introduced us to last week, right? With the infrared technology?
Yeah.
Is that her? Yeah.
Yeah, today's...
for a second, I thought you said Mary Lou Retton. But wait, no,
is she a gymnast?
This isn't gymnastics.
Yeah,
this is mental gymnastics.
Yeah, man. This is that's funny. That was a long time ago, man. I think I was a kid when she was doing the Olympics.
Yeah, see, I'm showing my old ass age.
Too funny.
Yeah. All good, man.
Yeah, man. So anyway, I guess we're done, right? I love you guys. It's been great hanging with you this evening.
Yeah, we had fun.
Yeah. Great guest. Good times.
Yeah, it was a great guest.
Awesome.
Great time tonight. Love you guys. Kick ass, take names, and when you feel battle fatigued, just shrug it off. That ain't battle fatigue. You just need a snack. Or
take a walk.
Nice cold iced tea or something. I don't know. Well, y'all have a wonderful morning, evening, afternoon, wherever you are in the world. I'm going to be back here in about 5 hours for PSB AM. TMC, hit it, man. Love you. Man. See y'all later.
Good night, Salty.
Night, sleep. Good night, Tatiana. Good night, YouTube and D-Live. And you have a wonderful show, TMC.
Thanks.
See you all.
Enjoy TMC. I'll be listening, man.
Love you all.
You guys. Cool. Hold the line. Pray.
You bet.
All right. So we're going to get rolling, and we're not going to necessarily do this in chunks, so to speak, because our platform is migrated. So we're going to listen, and when something comes up, I'm going to share with you my thoughts, and not in the way that this lady's talking about. We're on episode 94, Mary Lou Jepsen Towards Practical Telepathy. It's from the Long Now Foundation, and keep in mind, this was published over a year ago. It only has 2,300 views, and I want you to bear that in mind as you listen to this, because these are the issues that are going to be affecting our freedom and the conscious space going forward. Yet, this has only been viewed 2,304 times. So we're going to multiply that greatly tonight if you stick around. So I encourage you to do so. Here we go.
I'm Stuart Brand from Long Now, and my wife and I live in the houseboat community in Sausalito on a tugboat, which we think is pretty salty. Yesterday, a voice came from the water, and it was tonight's speaker swimming by from her houseboat 3 docks over. I also just learned that she swam the Escape from Alcatraz race this June, and that is salty. A lot more than we can do. She's been basically bringing machines closer to our senses, closer to our mind for years, and now she's swimming upstream to bring machines a lot closer to our brains. Mary Lou Jepsen.
It's great to be here. No pressure. Stuart Brand gave me a title for this talk, and I had to figure out the rest. So, Towards Practical Telepathy. Because it's, I think, a really important moment to understand what's happening in brain-computer communications. The fidelity is getting much better, much faster than I think a lot of you in the room may appreciate. And so with this lofty title, let me take a dive in trying to explain to you where we're going and why I think it's important to talk about it now. So I believe using the tools of our time, telepathy is in reach right now. And the tools of our time are big data, machine learning, and the often neglected trillion-dollar manufacturing infrastructure that makes today's consumer electronics, which is where I've been living and breathing for the last 3 decades, shipping billions of dollars worth of them.
Okay, quick pause. So today's consumer electronics, billions of units, billions of dollars, consumer electronics. That would be computers, cell phones, tablets, TVs, and on and on and on and on and on. And this lady has been developing chipsets and optics related components in that industry for basically her entire career. Anyway, here we go.
And the fidelity is going up. And I think that you're gonna learn a lot from this. But I want to start with something. Some of you might be thinking, why is this not Theranos? Why are we not a fraud? Seriously, you might not want to say it, but you might thinking, yeah, sure, telepathy came to the talk, but yeah, sure. And so let's just start there, okay? I've spent my entire life working on this technology, 3 decades, and I and my team and my investors will not ship a product before it's time, but we believe what we're inventing and creating can save countless lives and transform the lives of the living in a very positive way, which is why we're doing it. But we are not interested in the saccharine extrinsic results of a hyper-connected board, shipping product before it's ready, or the valuation of the company. We're in it to do it, and I just want to start there. So, thanks. So, you know, when I was a teenager, I fell in love with holography. This is very similar to the first hologram I made. I actually couldn't find it, but I went on and on from there. And the reason I mentioned that is because I believe holography is one of the 3 keys to enable us to have a high-resolution brain-computer interface. And so I spent the next decade of my career trying to make holograms not in film, but electroholography. And with a team of graduate students, somehow I found myself at MIT as a graduate student, we built the world's first fully holographic video system, all of us together. And I kept going with that, and this holographic video system is the crux of what we're using to see inside of our bodies and brains, upgraded 30 some odd years later. And so people talk about a world of screens, and it's just strange because I come from a world of screens, but I literally design the screens, like the liquid crystals, the transistors, the drive schemes, the devices they go into, the hardware, the software, every part of the system. And I've been doing that with all kinds of novel screen technologies for my whole adult life, from virtual reality to projection systems to HD TVs to wristwatch videos to all kinds of different 3D systems over the years. And one example of this, and one of the reasons I have some confidence to think that I can do what we're talking about tonight, is some work that I did when I was a professor at MIT, and I started a not-for-profit with my much more famous co-founder, Nicholas Negroponte, pictured here with the late Kofi Annan when he was head of the United Nations. And
so we're going to skip. She successfully created this one laptop per child and created a nonprofit business that grossed lots and lots of revenue. It's, I don't know. Anyway, it's not relevant to what we're talking about here. What I do want to reinforce here is that this lady has been in the R&D department, if you will, for chipsets and graphics and displays as far back as reasonable in history, right? 30 years. When we look at the technological jump and the miniaturization and the refinement of displays over the last 30 years, and this lady has been part of that. She's been one of the main thinkers. So we're gonna push forward just a touch.
And papers, but if you want to ship something, you have to work with the infrastructure. So I moved to Asia. And so this is like the factories that I've lived and breathed in. This is final assembly. When you take all the components you've developed and bring them together, I also work a lot in the factories that make different chips and components and so forth to design that, to get that functionality. So what else can you make with these things? As I mentioned, I left MIT and I did a startup, and then Sergey Brin kind of acqui-hired me in my startup, and I went to Google, and I thought, wow, what if everybody could have $1 million view or a shared screen to see and interact with their family in a different time zone? Wouldn't that be cool? And how would you do that? And I can't actually say what I did at Google, but I can write what patents are. And so basically LCDs, liquid crystal displays, are like $20 a square foot. And I figured out how to architect the liquid crystal displays such that you could just tile screens together and not see any boundaries between them. And then put a 3D into it so things would be at infinity. So you could all, have the view of the beach or the mountain or the Eiffel Tower, or whatever you wanted. And or your family in a different place. From there, I went to Oculus, and this is sort of the last trip because
Oculus is Facebook. So this lady went from MIT, she went to Google. Can't discuss all the wonderful things she did with Google. Similarly with Facebook, not able to discuss all of those things. Some of those things she can discuss to provide her with the credentials necessary to validate what it is that she's talking about. Major player, folks. This lady's a major player. Here we go.
a few years ago, about 5 years ago, virtual reality and augmented reality got hot again, and I had a lot of experience in VR, AR 1.0. And this is still like a face box, a face mask or a shoebox on your head, and that seems kind of large. So again, I can't say what I did at Oculus and Facebook because that's secret, but obviously you want, there's one thing that's acceptable to wear on your face and it better look like glasses or it's not going to have widespread acceptance. And so I figured out how to make an AR, well, I wrote a patent that Oculus owns, and lots of patents actually. I have like more than 200 patents in the last, I haven't counted in a long time, but like a few years ago I counted. So I invent a lot and ship the inventions, which is how I publish. And so this looks like a light-filled display. It's not. I use the old seamlessly tileable trick from my Google days on the back of your retina, and that enabled a VR AR system that toggles with the right resolution, with vergence control, and a lot of the things that you hear about with VR and AR as issues, which are totally solvable. But at that time, I and my colleagues at Apple and Google and Microsoft and Sony and Magic Leap and so forth were able to pull off something I thought was more interesting. We were able to put manufacturing process improvements into this trillion-dollar manufacturing supply chain at the sort of bottom of it. I sort of think of it as like this trickle down of Moore's law hitting the lowly factories that I've lived and breathed in the LCD fabs, liquid crystal display fabs, and camera chip fabs. And the discontinuity of Moore's law, the idea that Gordon Moore, the founder of Intel, said transistor density will double every 18 months, and that's been true for 50 years or more, really had a big impact and a discontinuity in the physics as the pixel size approached the wavelength of light. And that's why I mentioned the holography in the beginning. You can record a hologram if your pixel size is approximately the wavelength of light. Every single one of you in this room that has a smartphone has a camera chip in it with 1 micron pixels, which is the wavelength of light in the near infrared, and your body is translucent to the near infrared.
Did you hear that? She's telling you, without telling you, some of the abstract stuff that I think she's not allowed to talk about as it relates to her work with Facebook and Google. Infrared imaging of the body using something like your cell phone, which has pixel size resolution down into the nanometer range that is potentially embedded in the screens that we look at, that you're looking at. Here we go.
The visible is a little bit shorter wavelength. And I thought, this is just too big of an idea not to quit my job, my cushy job at Facebook, and try to figure out if I could make a system that could see in high resolution inside of our bodies and brains. So that was 2.5 years ago. I quit and started Open Water. Actually, a mutual friend of ours, Peter Gabriel, the musician, rock star, human rights activist, I think he called me like every week for like 6 months trying to convince me to quit, to do this outside of Facebook. So anyway, ultimately, he named the company Open Water. I actually didn't swim open water. I just started swimming open water because I thought it would be pretty funny for somebody that has a company called Open Water to swim open water, because it would just be really confusing. So I found it enjoyable. But the goal, what we're trying to do, is to take this big iron machine, this big MRI machine, and reduce it into a consumer electronics wearable. And that can transform medical imaging, and it can also transform the way we communicate with each other via brain. And let me take you on this journey and explain to you why I think so. I believe that we can put the functionality of that MRI system into a wearable, into a ski hat or a bandage or a bra or many different things that gives not just MRI resolution, but read-write and higher resolution at massively lower cost, not just in 10x lower cost, like with one laptop per child, but at scale, 1,000 times cheaper, which can be really transformative. And so why does that dovetail not just with medical imaging, but understanding our brains? Because our brains are part of our body. So if we can see inside of our body, we can see inside of our brains. And there's a lot of great work that I'm going to share with you tonight by these amazing neuroscientists using functional magnetic resonance imaging scanners. Those are like the video form of MRI, showing all kinds of things that we can communicate by just lying inside of these machines. So the national academies have said of the top 5, the national academies of most developed countries have said of the top 5 things you can do as a technologist, reverse engineering the brain is one of those things. And so the question is, how do you do that? So in the last 2.5 years, I'm not a neuroscientist. I've talked to a lot of neuroscientists. Any neuroscientist worth their salt will tell you, we don't even know what a thought is. I'm like, it's sort of like pornography. You know it when you see it, but we don't know what it is. And this whole issue boils down to something they call causal versus non-causal. You have about 100 billion neurons in your brain, each of them with 100,000 possible connections. And it just seems intractable to track that. And that's just the neurons, let alone the glia and whatever's happening in your gut and the hormones and all of the stuff going on. And then there's the non-causal approach, where you just do a top-down approach, which is really, I think, what's happened with some of both the implant solutions and the fMRI solutions. And so I think that there's this context that the bottoms-up approach is pretty cool, but the top-down approach is also pretty cool, and hopefully we meet in the middle. And so I want to talk to you a little bit about what's been done with fMRI.
So bottom up, top down, right? We're looking at the mechanics of thought, from the origination of thought versus just reading it and trying to decode it and understand it. So that's what she means by top down and bottom up. And neuroscientists, what she's alluding to there is that they're trying to figure out the components and the subcomponents of why thoughts become thoughts, and the distinctions, the differences between why to create the different thoughts. And she's taken the other approach, building machinery that is able to just read what's going on. And then she's talking about eventually having those two disciplines sort of work synergistically together.
In 1991, got the cover of Science, a group at Harvard Mass General Hospital was able to show that the blood flow of your brain as measured in an fMRI machine could show whether you were looking at an image or not. First thing, amazing. Oh my gosh, can we use fMRI to see thoughts? Well, if we fast forward a number of years later, I became aware of this work. This is the work of Professor Jack Gallant at University of California at Berkeley. And he started working with lab rats and then macaques, and then moved up to using graduate students as lab rats and put them in MRI scanners for hundreds of hours and made them watch YouTube videos while recordings were made of their minds lighting up or not lighting up, area by area. What fMRI measures is oxygen use by looking at the color change or the change of blood properties, whether it's carrying oxygen or not under a huge magnetic field. And by looking at that and creating a library, if you will, of students reacting to hundreds of hours of YouTube videos, then a new clip was shown called the presented clip here. And the computer, using the scan data, inferred what it thought the student was looking at. And the result is a grainy image of what the student was looking at. And I saw this and I'm like, oh my gosh. We just have to lower the size of the device and up the resolution, and there you go. And I tried to get Google to fund this. I tried to get Facebook, but anyway, I am doing it now. I'm a startup. So it's been a long haul. Also there's this Japanese group who went even further. They put the graduate students in the MRI machines and woke the students up a couple of minutes after they fell asleep, asked them what they were dreaming about to make a video of your dreams so that you can dump your dreams in an MRI scanner to the computer. It's totally cool. This is back to UC Berkeley, and with less than 5% false positive threshold, by looking at an area or a signature of your brain, we can predict a word cloud of words you're thinking, in this case, numbers. In another case, there's a violence area, sex and violence area. So you could actually in the future imagine turning that filter down if you didn't wish to communicate thoughts of sex and violence now that you're hooking your brains up with each other. So this
less than a 5% deviation, being able to understand words and basic concepts out of your brain. And she's building systems that are going to image orders of magnitude better than fMRI that's going to be available in something like a Rite Aid or a CVS.
This is pretty cool stuff. And there's some work done. This work is a decade ago. This is just a very fast path through fMRI where the students were shown 1,000 images. And the computer could, if the students were shown each of the 1,000 images just twice, with 80% accuracy, the fMRI machine and the computer could decide or guess or infer what the images the student was looking at. And just to be clear, through random guess with 1,000 images, that's a 0.1% chance of happening. This is pretty stunning how accurate you can get in certain situations just using fMRI. So then there's a lot of work that's gone on with brain implants. And it's got to be pretty tough for you to have the brain implant. Has anybody ever had brain surgery in the room? I have. Okay. So I'm the only startup doing brain-computer communication that's not doing implants. I had a non-elective brain surgery in 1995 to stay alive. I take a dozen medications every day to live. You're going to do that if it's that or death. But I just don't see a billion people having elective brain surgery anytime soon. It's the hardest thing I ever did in my life. But yet, here's a case at Brown University, my alma mater, where a woman was a paraplegic. They gave her an implant, and for the first time, she could give herself a drink with a robot arm. totally cool. So if you've got a condition where you're lock-in or you can't move, I totally see it. There's been this amazing work done with electrode probes where 500 neurons were activated in this primate, and with those 500 neurons activating with the electrical pulses, the primate could play the video game and do pretty well. And then they hooked 3 primates together, each with 500 electrodes. And the 3 primates played the video games a lot better, which is really kind of interesting if you think of where that might lead with sharing our minds. And so the bet I'm making, is that the massively more data we enable by putting a 2-ton magnet, that's the most expensive room in the hospital, that costs a few $1 million, that has liquid helium to cool it and a power plant to run it, and the magnetic shielding and no metal and all of that. If we put that into a wearable, we can get massively more data. Higher resolution, which I'm going to talk about how, with better temporal response. And we also have found, and I'm going to talk a little bit about non-invasive, actually direct neuron read-write, and better hierarchical algorithms that we think we can develop with this.
Non-invasive reading and writing to individual neurons with better hierarchical algorithms. So the real value of what she's building here is the software, folks. And that software will be translated to other means and other mechanisms of delivery outside of the wearable components that will be the nucleus of her business. The real value is the software that's going to be created, trying to get her wearables to function the way that she's advertising these things to function. And that's where big tech will come in and implement and scale the deployment of the hierarchical algorithms that she's talking about. We'll get to those alternative methods of delivery when they bring these to scale, if they haven't already, today or Sunday.
Non-causally, sort of top-down, meeting the bottom-up people who are saying, we don't know what a thought is, there's 100 billion neurons, each with 100,000 different connections. We hear you. We also think it's important to come top-down. So we're replacing that big, honking, literally big iron machine with a wearable. And for the first year and a half, I convinced my investors to just, let's not focus on product, let's just look at the limits of the physics. Can we hit the resolution of fMRI, which is about 10 cubic millimeters? And then could we get to 1 millimeter, which is about the resolution of non-video MRI? We did that. And we found the limit was at a couple of microns. We could focus through skull and brain, simulated optically mimicking phantom of skull and brain, to a few microns, which is, it sounds like 1,000 times better. It's like about a 5,000th of a millimeter, but that's actually an X, Y, and Z. So that's 1,000 times 1,000 times 1,000, or 1 billion times higher resolution than MRI that our core technology is capable of. And if we combine that with work that's been done with neurons, we can see the optical changes in neurons before an electrical pulse proceeds down the axon in a neuron. That's because the ionic channels change and it causes the membranes to roughen. And when they roughen, they scatter, and we can see a difference from that. And it's also been shown that you can use near-infrared light to write the state of the neuron without even optogenetics. There's also the combination of the great work in optogenetics where you add a tag to a neuron where you can optically excite it. So,
okay, well, she just said that infrared light is able to excite a single neuron without optogenetics, meaning without genetic modification of your brain. It can be done without that, meaning your normal, unadulterated, unraped brain can be raped with infrared light. And if you were here last show, I showed you the video whereby your Face ID recognition basically sends out lasers to image your face, image the environment. And this lady talked about the development of that technology for augmented reality for things like Pokemon Go. And so the billion-dollar industry that she's referring to, where she's pulling from the factories, she's pulling the chipsets that are going into things like cell phones to do things like scan your face. And she's saying that these very same chipsets are going to be able to do things like image your brain down to sub-millimeter, down into only a few microns cubed, a few cubic microns of resolution, to the point that they can see an individual neuron, the membrane of the neuron, roughen up before it sends its electrical pulse down its axon to excite other neurons. Oh, and infrared light can stimulate your brain. And those things are on every cell phone. And you can't see infrared light, so you really don't know when it's happening while you're sitting there drooling, staring at YouTube. But we'll go on.
We think that we could get a lot more information. And so then we get to this question, and it's a yes-no question. Do we or don't we want to understand the brain? And you could say, no, we don't want to. I've had a lot of people argue with me, and I'm just like, well, really, the National Academies of most developed countries have said, as I said earlier, that this is one of the things you can do as a technologist to really transform. But we could decide we do not want to understand our brains or any other brains on the planet at all. It feels like burying your head in the sand. We might be too scared of it. But ultimately, I can't imagine how we don't want to do it. And so on some level, we're really all Stephen Hawking in that the input to our brains are pretty good. The eyes and ears have pretty high bandwidth. But what comes out, we move our tongues and speak or type. I mean, if I was a good dancer, maybe I could communicate, but I'm not. And, we're stuck with language. And what if we could dump the images, the raw emotion, the memories, the layers of music directly out of our brains into each other? What could we do then is a question. And then the flip side is, can we handle it? This is the classic Star Trek, the first generation. Spock was this guy who was half human and half, it was called Vulcan. It was very logical. And he'd get in these mind melds where he was the only guy that could mind meld, but he'd fall in a heap afterwards and not be able to work for 3 days because all of the emotion was just way too much for him. And so I wonder how we will be able to handle it as we are able to share these thoughts. And we're going to talk a little bit about the ethics of that. So where are we today? I've explained a little bit about that. And where can we get in 10, 20, 30 years is really a question. And I might be more pro that this can happen faster than some of you, but pick a year. It's going to happen. In 10 to 20 years, I think we'll see language decline and our ability to share audio and visual fluency increase, and emotional understanding of each other should increase with our ability to share this, the thoughts and memories that we wish, that give us this great joy that we wish to share with people. And then we become somewhat transparent. It's this last bastion of privacy, and how do we handle being able to see each other's thoughts and dreams? So even if you think,
and how would these thoughts and dreams, that is the last bastion of our privacy, how would they traverse or move around the internet? And what applications do you think in modern day would be used to connect to all of your friends and loved ones and business associates? And what do we use now? And where did this lady work again? Oh, that's right. Google and Facebook. That's right. Straight out of MIT. Well, not straight out, but from MIT. And what are they doing right now as it relates to privacy, transparency, honesty, accountability, adhering to constitutional law? And off we go.
Like, no way, 10, 20 years. Like, this is the long now. Like, pick a year. Like, these before the clock runs out or out, like, it's going to happen. It's inevitable. And, the big opportunity really might be ego and bullying and biases and power trips and stuff like that, because we can see through it, hopefully. So I think that as we think about connecting ourselves with high bandwidth, it's perhaps inevitable that we will only exist as part of a collective.
Now, that's a bold statement. It's true. But you have to define what a collective is. Is it a commune? Or is it a group, a society of individuals who willingly participate in a collective community? What I mean by that is being part of society. And that's fundamentally what every culture is to some extent, and it's expressed differently. You have a Chinese model, you have a English model, you have an American model, you have an Indian model, you have a Persian model, you have a Russian model. There's common fundamental human characteristics, common fundamental human components in a society or culture, but then there's these wild divergences, very, very different expressions of participation in society. And if you're part of society, then by definition, you're part of a collective, but this is the redefining or the blurring of the definition of words that is so commonly used to make people feel good and feel like this is, something that, it's safe and warm and fluffy. So we have to get our minds, no pun intended, wrapped around this idea of potentially engaging in new and meaningful ways with each other through some variation or version of telepathy, where speech becomes just a subcomponent of communication. It is not the only way, or the primary way, or the dominant way. It is just another way. Yet maintaining our individual sovereignty, our individual privacy, whereby these systems are tools that the individual gets to employ at their own discretion and not at the discretion of Twitter, Facebook, Google, Apple, Microsoft, Amazon, and all of your major telecommunications companies, because they are the ones that run the information around the internet. Everyone only focuses on the big tech, but you've got the big telecom who get the information from point A to point B. That is the other side of the parabola that makes up the technocracy.
And what does that look like? And how do we walk into that? The Native Americans have had this vision of making decisions based on what would happen 7 generations from now. But we're living at a time where in 7 generations, will any of us alive today recognize, if we could live that long, that as humanity, with all of the changes in biotechnology in front of us right now? And maybe that's the wrong question anyway. Isn't humanity kind of discriminatory? We're not the only living things on Earth, and isn't it the life cycle? And don't we care more about that as we become more connected to each other? So that's the vision. So, what do we want? This is San Francisco, so peace, love, and understanding. But, what do we got? We've got, power, control, ambition, ego. And how does that switch or change as our brains come online with each other? So do we use it to empower leaders, or do we even need leaders? Can we communicate without them? These are questions that we need to think about. But, we have gotten better. If you pick a year, 1,000 years ago, 10,000 years ago, it really was might makes right. And, now we have laws that, murder is a crime and stuff like that. So it's much better. But maybe the really big thing that we should be doing is working on, the innovative solutions to big problems with really big impact. And that's the most valuable thing in the world. And by putting our brains together, we should surely be able to solve these better if we could do that effectively. And so the world, they say, is only changed with small groups. What if we could make the groups bigger without losing bandwidth, like we do now? And what could we do then? And it said, primates only have 3 times less connections outside of their family group than humans. And that study was done before social media. And yes, there are parallels and learnings we can have from social media here. Another thought I had is I was listening recently to an interview the fabulous Rob Reed did with Martin Rees, which I'd highly recommend. And in it, Martin Rees said, Darwinism was the survival of the fittest, obviously, but characterized by 2 things. Intelligence and aggression together survive. And as we connect our minds more together, does connectivity trump, sorry for the word, aggression? And that's the opportunity or the lack of one. So to open water and what we're doing, consumer electronics, big data, machine learning, this is some of what can happen with it. I did a startup because universities, well, I got thrown out for shipping stuff. Like universities ship students and papers, anything else is a product. You can't do it, I want to do it at scale. I use the $1 trillion manufacturing infrastructure of Asia, which means I have to ship. Big companies, the big powerful companies are really the ones that today are really known for optimizing click revenue for ad sales, and they're really good at it and made everybody a lot of money. But the decisions are made by people that are really good at that in web services, and so things on the fringes tend to require almost unanimous decision by the stakeholders, and there's a lot of politics, sort of the lust for power and control that gets in the way, and startups are just so simple. You just go down to Sand Hill Road, somebody gives you money, there's more money for startups than ever before in recorded history, and then you just execute and you show what you've got, and somebody else gives you more money, and it just seems like a simpler structure to get going that's just faster and more efficient. So we're trying to use a startup structure to do the innovator's dilemma, classic Clayton Christensen that says, honestly, those big MRI machines haven't improved much in 30 years, and the trickle down of Moore's law hitting these camera chip fabs just seemed like a really important opportunity to explore. And so I'm going to show you a little bit about how this works over here, because we use basically red light to see inside of our bodies and brains.
All right. Time to pay attention even more, because this is the mechanics of this is important, and it translates to microwaves. So just watch.
And yeah, I've got a little setup here. So if we can turn down the lights for a sec. I just want to show, maybe I'll go over here. Our red light goes right through my hand and my body. So does X-rays, so do gamma rays, so does a 2-ton magnet. But guess which one's cheaper? By a lot. So special for the long now, my husband and I found a place with brains yesterday, pig brains. So I have a trigger warning. Is anybody a vegetarian? No, seriously. So I got brains because I wanted to show you, since we're talking about brains and it's Halloween. So this was Petaluma yesterday. And I was really surprised. So this is a brain, and this is 2 pigs' brains. And I've got some more back here. But I implanted a tumor backstage. Can everybody see the tumor in the pig's brain? It's the dark spot. So what this shows is that you can see tumors with just red light. But I have some more brain here. And if I put it on top, I'm just spreading it out. It's really, you can no longer see the tumor, and it just, the light scatters everywhere, and in order to be able to see the tumor, we have to figure out a way to descatter the light. And the key to doing that, and why I mentioned holography, is holography. It enables us to record the intensity of the light, the phase of the light, light's a wave, at every angle simultaneously, including at every angle of the scattering of the brain or the body. And so we use that, and a third key, ultrasonic pings that are now we can make in chips. And so this picture of this head, these 3 discs represent the camera chips and ultrasonic chips and light that we're making, the new kinds of lasers that we're making. And from one of these discs that represents the ultrasonic chip and the camera chip, an ultrasonic ping emerges and focuses down to a spot. Then I'm gonna let the light in, and you're probably wondering, well, why the light later? And it's like, it's a very simple reason when you hear it. The speed of sound is slower than the speed of light. And so we want them to end up at the same place at the same time. So we bring in the light, it scatters everywhere, like the brain or like through my hand. And the light that goes through that focus of the ultrasonic ping changes color ever so slightly, just like the pitch of a police car siren changes as it speeds past you. It Doppler shifts. And so we exploit another property of holography, which is only 2 beams of exactly the same color light can record a hologram in interference fringes, which is really what one beam can't record a hologram. You need to beat 2 beams across each other. And that creates this fringe structure, which we decode. And we decode that fringe structure, much like Rosalind Franklin decoded this iconic image of X-ray diffraction to reveal the structure of DNA for the first time. But we can do that at 1 million times a second because we're using camera chips and electronics and not film and so forth. And so then we take another black disk and focus another ping down. And in fact, using this principle, we can scan out spot by spot, voxel by voxel, a 3D pixel of the brain, raster scanning row by row, or randomly in different ways, or focusing on areas of interest. We can do it with large foci or small foci. And this enables us to scan both the brain and our body. So you're probably thinking, what about skull and bones? And so this is real human skull that someone on my team got at skullsunlimited.com. Yeah, I know, we have fun in the lab. This is just red light, goes right through. Those of you who are in optics know, black absorbs light, white scatters it, so it just scatters. And so we use that. And with that, we've taken phantoms like this, where we implant tumors, and we can find the tumors, the vasculature that has the same optical properties as flesh, and we're able to find things with the same optical properties as tumors and vasculature and so forth. And so we've been doing a lot of that. We used to use whatever was on sale in the meat market, and some of the team protested because the lab started to stink a lot after we run a scan overnight. So anyway, we're finding different tumors, and this is super key. Here's a flask of blood, which you can see. And what's really interesting is red light, the blood is absorbed. The blood absorbs the red light. And if I compare that to my pound of flesh here, it scatters it. So you can see the difference of that, and so can our camera chips. And that's super important when we think about our bodies, because any tumor bigger than 1 millimeter or 2 in size steals blood and grows vasculature, so it can grow and try to kill you. So tumors have 5 times the amount of blood as normal tissue. So that's a top killer, cancer. Cardiovascular disease. We're really good at seeing where blood isn't, like in clogs in your heart or veins or so forth. And really importantly, the color change blood makes, whether it's carrying oxygen or not carrying oxygen, which is exactly what fMRI, functional magnetic resonance imaging, does, which is where I showed you in the beginning, throwing graduate students into those machines, we could read their dreams, the images in their head, the words they were thinking of, and so forth. So we can do that literally with camera chips, a laser, and ultrasonic pings.
Okay. So they're able to look at the blood. All that said, it was a lot, and I didn't want to stop in the middle of it. She's able to use holography, where you have coherent light, two different light sources intersecting at a particular location, use ultrasound to change the frequency of light at a particular location. What that means is that they're triangulating. So they're able to triangulate a piece in the brain down to a few cubic micrometers, what she's calling a voxel. It's really a cubic millimeter, but she said earlier it's actually smaller than that. They're able to scan like a TV, old school TV scans top to bottom to populate an image. They're able to scan left to right, up or down. They're able to focus on particular points in the brain. So what they're talking about is having a steerable phased array system that's able to triangulate with more than two sources of light and or more than two sources of ultrasound very, very quickly, rapidly, microsecond, potentially nanosecond, scanning of your brain. And they're looking at blood flow and or change in blood, meaning the oxygen content. And so when your brain is working, it uses more oxygen. And so it's going to change the color of the blood, which means it's going to change the light absorption properties. And that's what they're getting back. They're looking at the hologram that's created, but once it's bounced off of or passed through tissue. And so when that happens, it scatters, the light scatters. So they're reverse engineering, they're reverse creating, reverse imaging the light after it's interacted or gone through tissue in the body, or in this case, the brain. And they're able to reconstruct it. And from the reconstruction, figure out what's going on intelligently, up to and including being able to read your brain better than an fMRI, which she's illustrated that over 10 years ago was able to do things like upwards of 80% accuracy, understanding what words were in your mind and or particular emotions. And she's talking about doing that millions, if not billions of times better in a wearable, something that's going to be cheap and available in a department store near you. Most of that improvement is with software, because she's talking about using existing chipsets. Stuff that's in your phone and your tablets today will be the primary components used to send and receive energy into and out of your body for high definition resolution, up to and including full telepathic communication. So there's all of that in a nutshell. Let's continue.
In the form of a wearable. So this is a mock-up of what our system can look like, and you can wear it here, around your head, different things. We also might go with a wand kind of system. You know, we're working on different form factors for that. But the physics is pretty solid. There's also something with fMRI. It often takes 4 seconds to see the use. What we're looking at is where oxygen is used in your brain, as I mentioned, and that's basically the blood flowing by, the oxygen gets pulled off, and then they call it deoxygenated, no more oxygen on the blood. But there's a dip that happens first, so we should be able to see a sub-second response. We're also looking at neurons, as I mentioned, which move at a millisecond kind of time frame. And so we're combining all of these to see what kinds of systems we can build. So last winter, spring, we had this big lab rig setup where I work with this fantastic team. I'm up here tonight, but I really, the work of all of the team that I work with is astonishing. Best team I've ever had the joy to work with. We built this system, and we built it because before you, as a chip designer, when you design chips, you need to spend millions of dollars to get access to the fabs, and if you don't ship those chips in short order after designing them, you're thrown out of that lab. And so what you do is you jerry-rig whatever you can using existing chips, so you can test every aspect of your design with a big rig first and make sure your system will do what you think it does. So we spent 2.5 years doing that. And now what we've done is we've collaborated and made these new components with partners, 3 new components: camera chips, ultrasonic chips and new kinds of lasers. The camera chips I talked about, the 1 micron feature size is key. What happens is the light in, the infrared light that comes in is converted at 70% efficiency to electrons. That's up 10x in the last year alone, and that's become standard in smartphones to do 3D sensing and for next generation augmented reality so that you can play Pokemon Go plus plus. No, seriously, that's why $1 billion was spent to do this, so that you could play Pokemon Go plus plus. And to unlock your phone by not, typing a password or swiping a pattern. But I thought that maybe we could use it in a different way. So we are, and it's also very good. Do you know how many lasers are in this generation iPhone? Close to 500, because they put dot and line patterns on you to figure out what your face looks like. So we can just use that to enable telepathy and to massively lower the cost of medical imaging, which I thought might be more interesting.
Okay, well, you heard it from a lady who's likely developed that stuff, right? The very thing that they put out for Pokemon Go, for augmented reality. So you've got lasers in the back of your phone, lasers in the front of your phone that you can't see, to unlock your phone and to play cool augmented reality games, are going to be used for telepathy and advanced medical imaging. And they're sitting right next to you. So the benefit to all this, the real plus, not to take away her Pokemon piece there, but the real plus to all of this is that if this is done properly, you have a proverbial Star Trek medical imaging device, and you already own one. And this, to me, is one of the major reasons why I think big tech and pharma are merging, is because we've reached this point where technology and energy-based medicine is on the cusp of displacing chemical-based medicine. And so these industries are merging. And in the process of that, there are many other useful, fun little applications, like stealing your thoughts and theft of intellectual property and complete and total omnipresence and thought police and pre-crime and social credit score and complete and total technocratic rule. Hashtag Constitution on fire. Big tech doesn't give a shit about your constitutional rights.
And it's not like, look, I liked shoot 'em up games when I was 15 too, and I worked with a lot of people at Oculus that still love them, but I just, it's fine, because it's enabled us to get this technology available. And the ultrasonic chips, that really, I think the first time that came into my consciousness was some work that Texas Instruments did in the early 90s to make screens, projectors, so that you could plug a laptop into a projector in a boardroom rather than printing out your slides. It used to be you'd have an overhead projector and what they called foils, which were pieces of plastic that were printed on, and you'd project your talk that way. And what Texas Instruments did was make pixels with little diving boards on each pixel that were electrostatically deflected. So that technology now, 30 years later, is enabling us to ultrasonically vibrate and focus with these chips that we can make in any fab that can steer around plus or minus 60 degrees to allow us to focus into the head and change the wavelength of the light.
Yeah, so that sounds like, well, what the hell is all that? I don't know anything Texas Instrument-y, and I'm, that's a corporate thing. No. So you remember the iPhone 5 where it had the little circle on the bottom and you had your thumbprint on there and you could unlock your phone with your thumbprint? Yeah, that's ultrasonic technology. And your screens have it now because you can unlock phones with your fingerprint using light or with ultrasound. They can generate this stuff. It's called surface acoustic waves, if you want to look it up. And these patents are all over the place with Apple and others. And these are totally tangible, in use, clean, respected technologies, for crying out loud. They're used to authorize things like payments from your phone. or to get you into your phone. And she's talking about being able to use these very same things to then project ultrasound into your brain. So if it's that easy to do, and we know about the photoacoustic effect or the thermoacoustic effect, the photoacoustic effect is the excitation or the thermal expansion, the heating up of tissue using light, and that's photoacoustic. The thermoacoustic effect is the use of radio waves or microwaves or millimeter waves to expand tissue to then generate sound waves in your body. You have the ultrasound right there, folks, with the microwaves, with the millimeter waves, with the radio waves. You have the ultrasound right there. The question is how easy and how well can they focus it? And well, we're all around screens all the time now, so there's your light source, especially with these new, 500 plus laser chipsets that are projecting a dot pattern on you so that you can, get into your phone without typing in a password. So, off we go.
The other part, one of the reasons we've scanned mostly dead animals, whatever was on sale at the meat market, or optically mimicking phantoms, is because we're alive. It's good to be alive. That means we move. We breathe, and blood moves through our veins. And that's the thing that we have to do a flash or a strobe faster than the blood moving through our veins. Although I'm friends with this professor in the Netherlands that has graduate students put tourniquets on their arms to stop the blood flow so that he can take images with normal lasers. But if you did that on your neck, it's called strangulation, and it really won't work. So we did the hard thing. We made a pulse laser with the right, what's called coherence, very, very fine control of the colors. So when we shift the color, only the shifted color interferes, not the unshifted. That's called coherence, and at the right wavelength, so we can pick up the color change in blood, whether it's oxygenated or not. So we've made those, and we also, like in the last 6 months, we've lowered the amount of light we need by about 10x. We've increased the image quality as measured by the signal-to-noise ratio, which is a technical term, but basically you want more signal, less noise, so that's good. We've reduced the footprint down by about 100x, and we're about to, in this quarter, increase the scan speed by about 100x. And so the system in build-out right now is in a small animal facility locally at a secret undisclosed location where we've actually slimmed it down to just a little ultrasonic array, the optical detector camera unit, and a little fiber optic probe that comes in on the rat. Total ethical approval to do this. All of our tests are checked. And our goal this quarter, next quarter, is to MRI these little rats and then image them and make sure our images are the same or better than the MRIs. And then we'll get approval for human use. So this is super important, not just for telepathy, I keep mentioning, but it bears to mention again, 2/3 of humanity lacks access to medical imaging. It can be transformative to let us see and diagnose conditions earlier and treat them earlier. But everyone in this room say, well, that's, poor people. Well, it's true for rich people too. We know MRI is a better diagnostic, about 10 times better for breast cancer. But do we use it for routine screening in the US? No. Is it used in any country in the world? No. What's the number one reason why? It's too expensive. So if we can lower the cost of it, then people worry about false positives. And it's like when the scan costs less than $1, you can scan all the time. You should be able to buy this thing in the drugstore and just scan. If you've got the BRCA gene, do you have to go all Angelina Jolie, or could we make a bra where you're like cut off part of your body, and it's serious stuff. Could we just look at, over time, the deltas? You care basically about 3 things. Is it getting bigger? Is it getting smaller? Is it staying the same size? If it's getting bigger, you might want to seek active care, but if it's something, you can just watch it, which is very different than what we have now with the cost structures involved. There's also a limit to how much gadolinium you can have, which is the contrast agent that's injected for an MRI scan, and it's thought now to cause cancer, and people are trying to figure out what that means for lifetime scans. Obviously with CT and PET, there's radiation there, so you're also limited. So then the other thing, the most expensive healthcare in the world is that for brain disease, which 2 billion people suffer from if you add up things like schizophrenia and depression and neurodegenerative diseases like Alzheimer's and Parkinson's. And this could do enormous good for that. Like there's a biological basis for brain disease. Right now, to diagnose depression, where the average person loses 12 years of work in their life that's clinically depressed, you answer these questions like, have you gained weight? Are you sleeping all the time? Are you tired? Do you have thoughts of suicide? You answer to that, yes to that and 50 other questions, you're clinically depressed. Where studies have shown that actually the way what your brain looks like in MRI is an indicator of what kind of depression or if you have depression. And from that, you can see what the therapy does. Does this pill work to change that pattern or not? You can see that much more efficiency. You can close the loop. Precision psychology.
Wow, that sounds real fun. Precision psychology, something that remote diagnostics and telemedicine, and kind of fits the mold of where it is the entire world is going. Connecting together while you're alone. Remote diagnostics, being able to understand or be classified or diagnosed with a mental illness just because of whatever, and having AI do it, or a medical board that is deploying software over the internet to observe an entire population. Do you see where this is going? That's a possible future. In my view, it's a likely future, because that is what a technocracy would do to project enslavement upon the species.
Could be enabled through this. And then Peter Gabriel, who I mentioned earlier, I just want to, as we sort of start to bring this together, we're doing imaging and also some writability that I'll talk about. But if we combine this with all the great work being done in genomics and blood, is there a way, Peter asked, and I think he's started, and he's announced this thing that he started called the TAP, which is a way to think about, he talks about the music industry fundamentally changing when streaming music happened. A, music got cheaper, but B, everybody got access. And so how do we get everybody to have access? We probably do have enough doctors. They're not evenly distributed. There's 3 continents that lack enough doctors, and yet smartphones have happened and all of this stuff. So how do we sort out what that looks like? And I'm so glad he's taking it on. We're helping him every way we can. But one thing that didn't occur to me, the Focused Ultrasound Foundation, I was just there last week, helped me understand that these sonic pings, where we're focusing down for a microsecond and then we shift the wavelength of light, if we just focus that for 15 seconds, we can do surgery without a knife. We can ablate tissue. We can open the blood-brain barrier. We can do neuromodulation. We can deliver drugs, sort of like microdosing, but the right dose at the right place and not getting the drug everywhere else, by using drugs that are basically microencapsulated and the ultrasound bursts them.
Yeah, so these fun and friendly little things that are going to be on your head, if they just continue to pulse for a longer period of time, it can do things like open up the cell walls, your neurons, open them up, like melting your fucking brain. Ablating tissue, that is a surgical scalpel without the knife. So you're not dealing or treating tissue from the outside in, you're dealing with it from the inside out. But you're still achieving the same thing. You are rupturing, opening, carving, cutting with ultrasound. And she's saying that with her stuff, you just apply the ultrasound for a longer period of time. And what does that look like? You get the right resonance and you start rupturing brain cells.
And so this is approved for essential tremor, for treatment of Parkinson's disease. The recovery rate, if you don't, guess what? If you don't cut open your body and bleed out blood, is much higher. And so it turns out that from where I sit, that's like, sorry, I'm an electrical engineer, that's a packaging problem if you want to put in that much power for 15 million times longer than we are, but it's at the same basic power density. So we're very excited about that. On FDA, we're in some informal discussions with them, but the predicate products that have existed using near-infrared light are for many decades, as well as ultrasound. You are exposed to more infrared light today on the streets of San Francisco, even in the clouds, if you're in a foggy part, than you will be with our system, and the ultrasonic pings are well understood as well, so we don't anticipate much of a problem while we're walking through it. So what this can enable is the democratization of healthcare and telepathy, which brings me to tonight in Stuart's title, because they're not separable. The same device can do both. The software layer is different, but the same device that sees inside of our bodies can see inside of our brains. And so in terms of the limits of speed, we can go up to 100,000 frames per second per unit, and we can multiplex them, which is way faster than MRI, although our first units will be substantially slower as we walk through developing this. In terms of depth, we had gotten to 6 inches, but then we upped the laser power. It's really a function of a laser power. So if you think about an obese patient, the limits from the FDA are basically how much infrared per centimeter squared. And this might sound cruel, but an obese person has more surface area than a skinny. So you can basically irradiate, you can bring in more light and get more depth. So we think about a foot from any side. We're walking through that right now. Resolution, we can match fMRI, we can go smaller. We could even go, as we showed in the lab and live on stage at TED this year, we could get a few micron resolution. The blood time scale is about 4 seconds. We think we can bring that down to sub-second, looking at the dip, as I said, but there's also the neural time scale and how many neurons we scan over the course of milliseconds as they beep. They send electrical pulses. I think of them as sound. And we're not working on causality. Not all 100 billion neurons are saying we can come from a top-down approach and meet the bottom-up people. And it reminded me a lot as I was preparing this talk of talks I had with the amazing Paul Allen, co-founder of Microsoft, founder of the Allen Institute, who died too early a few weeks ago. And he always used to tell me I was nuts, which I always like talking to people that tell me that, because I tend to learn something, especially somebody as smart as Paul. Such a great loss. But he would always say, there's 5 Nobel Prizes just to understand how a neuron works. And I'd say, great, Paul, you guys go get those Nobel Prizes and we'll meet you halfway. And there's just this monoculture of neuroscience that you've got to understand the electrical pulses down. Then I'm an electrical engineer, I get it, but there's all this stuff you can do with optics and physics. And in fact, that is what we're using for imaging systems. It's the physics breakthroughs that have enabled us to see through our bodies. So the best argument I heard, a friend sent me a paper, who shall remain nameless, saying, what you're doing sounds like, this is again the causal approach. There was this classic paper written 2 years ago about, a neuroscience approach. Could it work sort of decoding what was happening on a silicon microprocessor driving the game Donkey Kong? And could you probe out the transistors and figure out how Donkey Kong worked? And they tried to probe them out, and then they zapped a transistor at a time, and the result was they couldn't figure it out. It just didn't work. It's a pretty cool paper. But they do point out in this paper the brain is more modular. And so we still know with 80% accuracy what image you're looking at. With a 5% false negative, what kind of word cloud you're thinking of, just from existing resolution of fMRI scanners. And so the implications are profound for that. Again, we're not trying to say we're doing causal, we're doing non-causal. And there's...
Okay, well, there are the stats again. So when you think about modern spying, modern wiretapping, modern surveillance, when they've had this capability of imaging with those types of resolutions for over a decade, you be your own, you be the judge, right? Figure it out for yourself. Come to your own conclusions. But it's gone way beyond just clipping onto somebody's phone line and listening with a speaker around the corner. pretending you're a phone man. It's way beyond that.
There's profound ethics with this. One question is, can you assume what someone's thinking? You can do that now, but we're not saying we're 99% accurate. So the question is, how do we filter? Have you ever had a thought you didn't want to communicate to somebody but couldn't suppress it? Yeah, so we're going to need filters. As I mentioned, the sex and violence filter people are working on, but, other filters, because, we don't want to be rude. And then what do we do with the data? And we were talking in the green room before about Eleanor Ostrom and the work she did in land trust. She's the only woman that won the Nobel Prize in physics so far. And she really worked on, as we think of having all of this data, how do we deal with it responsibly? Because what I think is going to happen is it's going to start with low resolution grainy, and it's going to get better, and then all of a sudden it's going to be really great. And then what did you sign away with your data before? Like what, we've seen this movie before with social media now, maybe. So how do we get smart to that and talk about that now and form the right construct to how to deal with all of this data? Because we'll have lots more with success. Imagine we have way more medical imaging data than everything that exists to date in, pick a number of years. Again, I think it's a single digit small. You might think it's longer. But how do we define the rules for this? How do we deal with trolls? Or is there an effective way? And why belong to this? And Eleanor Ostrom showed, there was a famous paper called The Tragedy of Commons that was written that thought somebody could just buy extra cows and overgraze the grass, and there'd be no grass for anybody, or the use of water. But the examples shown in Bali or in these small communities is that they actually had very good ways of handling it, and it's locally and talking. And I think this community might really help us figure out the right way to go about this. But it's our job to define what it means to be responsible before we ship a product, which is why we're talking about it here. Legal proceedings, of course. The answer is no. However, there's a book called I Know What You're Thinking, which shows already how fMRIs have been used to incarcerate people in various countries already. So privacy, just a question. Do you think you'd be more private if you had an implant or if you could remove something in the form of a wearable? Should be obvious. So the apps, I'm just going to go super quickly. Brain body, can't separate. A movie director, suppose you're a movie director and you wake up with an idea for a new scene that you were going to shoot that day, but you had a new idea. Could you just dump a rough cut of it directly from your head, show your team and say, I know we're going to shoot that other thing. This would be so much better. Can we do it? It's a fast way to communicate visually for so many people. Enhanced social media is obviously another application for this as we think about really setting our brain to rest mode. We know that seems to be the cause of a lot of mental disease. People meditate, but is there an easier way to do that? And could we enable that? Dumping the words out of your brain without having to type seems very easy just from the center of where the word center is in your brain. A lot of people ask me about gaming and digital therapeutics, and there's great work being done on that. I think it might be an interim solution as we get to more of I don't know if we need the games anymore. I know maybe that's controversial, but can you erase thoughts, bad memories? Maybe, but you could do that now by zapping part of your brain, and there's some implications. If the brain, we do deep brain stimulation already. Don't know. Brain after death? It's a lot easier to record while you're alive, especially if you're looking at blood flow. But a lot of people ask me, we don't know. We don't know how to do that, but to share the joy of a memory would be pretty amazing to do with your grandkids, or to capture that and share all of the emotion of it. This might be the biggest moneymaker of them all. I think people would pay anything, and you know what? It doesn't have to be that good. Really, to start, even just knowing your pet, your dog or cat was anxious or was hungry or wanted to walk, it'd be pretty, didn't like that other dog, like that dog, it'd be really helpful. sex and intimacy. I mean, right now, we stroke body parts and release oxytocin. What would happen if we could share the joy, the emotion, the vulnerability, and so forth? And do I need to go further? Maybe over drinks later, but you get the idea. I think this is inevitable. It's really inevitable because of what's happened in the trillion-dollar manufacturing infrastructure, machine learning, and big data. I think it's inevitable. We hope that we are the company that enables it, but more importantly, we want it to happen, which is why we're talking about it, because it's important it happens. People are dying. So, if you're a doubter still, do you really think having more data at higher resolution, at better temporal feature with read-write neurons will not give us more information to understand this, especially as we massively lower the cost and put it in a wearable rather than the most expensive rooms in hospitals? So, and again, it's inevitable because you could even say, no brain-computer interface. We just can't deal with it. We can't deal with the ethics. But in the case of what we're doing, it's the same hardware layer that can see inside of our bodies and our brains. They're all biological. And so it's very hard to separate. And so my question to you, if you buy that argument, what can we do to shape it? Thank you.
So here comes Q&A. There's some good stuff that comes out of this Q&A.
Okay, we're all going to just think about this for about an hour, and then we'll talk.
Okay.
One thing I didn't get, which is I sort of get how the brain reading part goes. How does the brain writing part go?
We can neuromodulate with a focused ultrasound at a longer amount of time, and that's very helpful for brain disease right now. But we can also do that with neurons and change the state of neurons. And so that gets to the causality. We can write the state, certainly with optogenetics, which is the tag of an optically sensitive part where you're genetically changing your material. But even without genetically changing the material, the indicators that we have are that, well, there's a lot of literature published that using infrared light alone, you can stimulate neurons or inhibit neurons. And since we can focus that light non-invasively through skull and brain and focus it to the diameter of the neuron, we're making the leap to say, we should be able to do this.
So there you go. Expert in her field says that infrared light can neuromodulate your brain. Infrared light, lasers, can neuromodulate your brain. So just how deep are those lasers going as you stare at your phone? Prefrontal cortex, temporal sides of the brain? We going down into the center of the brain where we get to the emotional centers? Or are we triggering more than one location of the brain? Let's say 3 centimeters in, 4 centimeters in, anywhere that light can go. How accurate is it after it bounces off a wall? How powerful is it after it bounces off a wall? Are they able to amplify the light waves by getting them to reinforce each other, just like they can do with electromagnetic waves that we understand, like millimeter waves or radio waves? Can this be done at the back of the head after reflections? Stimulating your brain, turning on or turning off neurons with infrared lasers after she gets done talking for an hour at this point, saying that she's using existing chipset technologies that are currently deployed in your mobile devices. And let's continue.
So presumably the first applications of that kind of writing would be medical, and what things come to mind, like Parkinson's or what?
Sure, deep brain stimulation is used for Parkinson's, also for essential tremor, other brain disease issues and mental disease. It's used there now, and it's FDA approved.
And then at the telepathy angle, as you're saying with the PET, it can be probably pretty low bandwidth, and both sides will fake it. With humans, well, it's interesting. I'm suddenly thinking of Marshall McLuhan and the difference between cold and hot and cool and hot, and he thought that sort of low bandwidth people like to like girls with glasses because things are a little vaguer, and then you can build in whatever you want to see with a little more vagueness in there. As this gets higher resolution, things are going to get awfully precise.
Right.
And you like that, and it's clear.
Well, I nearly died as a graduate student in an Ivy League school in the United States in 1995 because an MRI was too expensive. I didn't know I needed one. I was pretty entrepreneurial. I could have, but people are dying because they lack access to medical imaging. Yeah. The death rate, I was speaking to a family that runs a huge chain of hospitals in a South American country who said the death rate due to cancer there is 3 times that of the United States. And they cite the cost of medical imaging as the #1 reason for that. And so, yes, getting more resolution to see inside of our bodies and brains is interesting, and understanding how we work, and by the way, we're not the only thing with brains on the planet, seems an important endeavor for the living world. But it's not without repercussion of how misuse could come.
And it's interesting that resolution is both sort of spatial and pixels, getting down to bandwidth of light, but also time. I remember when virtual reality first came along, if there was any lag at all, it was disgusting and you threw up. Right. But once the lag got down to, you probably can name the actual number of microseconds, then that was no longer an issue.
Yes.
So this closer and closer to real time seems like an important part of the resolution. Is that right?
Yeah, it can be blurred. I mean, if we're using fMRI, it's over 4 seconds, and so slow, like thinking of images, but like how can you abstract the images that you're thinking of, or the music, obviously, which is very temporal, but you can think of it in terms of frequency space, for example, and then be able to dump that, as has been shown. But we can dump visual images out of the brain and slow-mo movies with motion compensation and so forth. It's amazing as you start to build what you can do with algorithm development. But also we can
slow-mo movies is interesting because then you're talking about the change of pace that you can do in terms of reading the micro movements and things like that. That really is a whole nother level of information.
As we develop these dictionaries of how we see. I mean, so much of the visual is back here in a certain area. We can go high res back there. And then on the temporal, can we get the dip that's the sub-second dip before it takes the whole, and you only have to go down a centimeter here. I mean, it's like, it's so much easier. And that, from an ultrasonic perspective, we can then do a tighter focus because the penetration of ultrasound is related to its frequency, and the frequency is inversely related to the focus size. So at say 20 megahertz, you can go down maybe 2 centimeters, but you can focus to a 20th of a millimeter.
Shall we?
And
Question.
you can pick up the light too there.
Yes, please. Micah Zworowski asks, what do you think is the best path to become an early adopter of this technology? Do they have to come work for you, or what happens?
Yeah, we're hiring. We're hiring lots. But so we're making alpha kits for next summer as we figure out our go-to-market plan. And then the following year or 2 later, we'll be able to ship. And that's when we'll be able to support a lot more people, because our first alpha kits won't be products. We won't have finished the UI and the UX and the ID and all of that. We're really focused on the physics and the signal-to-noise ratio and the depth and the scan speed and so forth. And so for early adopter, work with our company or one of the companies we're working with. We're trying to figure out how to reach out to the community, but we're a small company and we're really focused. And so maybe someone else, maybe you have an idea. Come work with us.
And you're working with these rats in the lab now, and say a little more about what reading and eventually writing means working with these animals. What are you actually sort of getting?
We're trying to exceed the resolution of MRI. And prove that with a living animal, because we just made the pulse lasers so we can do living animals. So I took money from Brooke Byers early on, and this is relevant because he made me make one promise to him. He found me, brought me into, everybody's heard of Kleiner Perkins, but it's actually 4 letters, KPCB. He's the B in Kleiner Perkins, and he came and got me into his office and says, look, I want to invest, and brought me a nice check, and he made me promise him one thing. I wouldn't experiment on myself or any of my employees. Too bad I had already promised,
Right.
but I have.
Right.
So we're doing the animals.
There's a lot
then
of
we'll do
volunteers
humans.
here ready to line up. I'm sure of it.
Can't do it, I promise, Brooke. So
Okay, noted.
it's smart of him, actually. So so we're in the small animal facility, and then we'll get a thing from the FDA saying we're okay in humans. We think it's perfectly safe. We'll prove it. And we just got the strobe lasers that enable us to do this on living things. So we're just getting our first images on living things right now.
Zowie. You describe this as a ski cap or a wearable or a bra or something like that. Say a little more about what's actually involved in wearing a thing which is going to get that kind of resolution out of the brain.
So, well, one thing is the hair. And so there's a small comb structure because the hair absorbs light, especially, okay, I'm just going to say it, anybody with dark hair, dark skin, we're testing that because black things absorb light more than white things. So you're easier, you've got less hair.
I'm good. Bring it
It's an
on.
advantage.
Well, it's a fashion, at least in males now, to have no hair at all.
Yeah,
so.
exactly. So that's easy. No, but it'll work for everybody. So we've got this, and you put it on, and the ultrasonic pings. So one thing I didn't explain is ultrasonic. Ultrasound is a different speed in bone as opposed to flesh, and so it distorts. And so we correct for that distortion with other ultrasonic probes looking at that so we can focus. And we focus the shape of that ultrasonic probe around, and we pick it up with camera chips that are literally camera chips that are being made at more than 1 million units a day that go into the world's smartphones. The ultrasonic chips are going mainstream in the fabs now, and we're making fiber lasers that are very typical. So we're using what Asia Inc. and the consumer electronic supply chain is good for to make these subcomponents that enable us to make something low cost that can fit inside of a wearable. It can be a wand as well, and that might be better. I mean, literally, if you're going to give something to a village.
The wand is both projecting and reading. Is that the idea?
Yeah, it can project and read, and that might be better in terms of hygiene rather than a wearable if you're going to share it across people.
What kind of power demand does all this have to do all that light and optics
Well,
and sound?
It depends. So it's a modular system. Each of those discs I showed over the head represent an ultrasonic chip and a camera chip array, a double stack camera chip array that has logic decoding in it, and then a fiber optic coming in and a Leica plate that brings in the reference beam to the camera chip. We can spread those out as many as we want, but the amount of depth and resolution is related to how much light we can bring in. And so we envision a small, medium, and large laser. So the large laser will draw more power than the small laser. One place we want to get into immediately is triage, ambulance, urgent care, places that don't have the power plant. And so we definitely want to be in the size frame that can work in an ambulance.
Is there,
and power as well.
What makes me wonder is, there's the sort of the portable one, there's the ambulance one, and there's the one in the big expensive room in the hospital.
Just the lasers are different. Everything else is the same. And Asia Inc. likes to make lots of exactly the same things. So that's why we just buy more camera chips and more ultrasonic parts. The laser, it's hard to gang up the lasers because of the very stringent requirements we have on the what's called the coherence, which sounds like a silly term, but it makes sure all the waves are exactly the same wavelength of light within a few megahertz, which is like 1,000th of a nanometer kind of coherence. And so it's very hard to gang up the lasers like that. So right now our approach is a small, medium, and large laser.
Fair enough.
And we have a really large laser that we've built that's it's big, but it allows us to experiment around and blast things and make sure we can see the limits of the physics.
Is the descattering, I mean, you did holography early on, and that's Fourier transforms and stuff like that.
Yeah.
Descattering out, is that just a nice off-the-shelf kind of thing now, or has that got to be pushed a lot further?
So the holography is enabled basically in the infrared by two factors that have come into being literally for 3D scanning and for Pokemon Go and VR and AR. And that is, they sound scary, two terms, quantum efficiency, which is light in, electrons out, was 7% in the near infrared until this year. Now it's 70%, mostly because you can unlock your iPhone with rather than a picture of Stuart Brand, and now it has to be you, and you're measured at 940 nanometers, where you're back. There's this window between 700 and 900 nanometers where you're a translucent blob of gelatinous blood and look like a jellyfish. And then you're back opaque at 940. That's where your iPhone's working and unlocking your phone. And it's got this laser light it's sending out at 940. It doesn't blind you. It's low. But the camera chip is looking for the signal of that laser light to catch the shape of your face, which means it's looking for a little ripple on a sea of light in the room. And so what that is called is a deep quantum well. And that's also what we want, because we're looking for a little sea of ripples in the hologram that we're recording of the wavelength shifted light over the huge sea of non-wavelength shifted light. And
There's a lot that she just said right there. Just understand that the physics behind what it is she's trying to accomplish with deep tissue imaging and synthetic telepathy those physics are used today for commercial applications like unlocking your phone and to drive and run programs like Pokemon Go, where the Pokemon, as you're using your phone, has to look like it's sitting at a particular location on top of a table or out in the real world somewhere, overlaid, augmented reality. So the precision, the 3D mapping, the spatial precision, those physical properties, the physics behind that already exist. They're already in use. They've already been in use for a long time. So you've had time to refine and understand and gather data and all that stuff. It's already been done. And she said that the iPhone projects at 940 nanometers, which is just past the point where we become opaque again with infrared light. And she's also saying that the ultrasound can wave shift the light. So can it shift it up or down? Can we go back to the gelatinous state and be imaged that way? And on and on and on. And we could spend 30 minutes dissecting her last 5 minutes of speech, but we're going to move on because we're running out of time.
So we can use, and most camera chips have red, green, and blue color filters on it. That doesn't work in the infrared because no infrared gets to them. So these small changes.
So it's monochrome necessarily.
It's a monochrome with a thicker silicon layer, so it can catch with good efficiency, the longer wavelength of light. That costs whatever, call it $1 billion to get it everywhere. But it is everywhere, and it's shipping at 1 million units a day in the thing the consumer electronics industry makes. And so I saw that, and I'm like, I loved Pokemon Go. I actually played it every day for a while. But, like Pokemon Go versus, transform medical imaging and a chance at telepathy was an easy choice.
And that raises the question of the signal that's coming out of this. Can you put on augmented reality sunglasses and see through your mice?
Maybe, but why not just extract what they're thinking? Why not communicate visually directly with their... Right. Is the best display, actually, because I've made displays all these years. We don't want to have to wear anything. Can't we just zap each other these thoughts and images directly, without covering our eyes? People don't like to have their eyes covered with anything other than what we're wearing.
That's true. You're right about that. Question from Nick at Longnow says, improved imaging of each other is great. This is what we're talking about. Better models allow us to focus on more nuanced things. Do you think that these models will ever be exhaustively complete? Is there sort of levels of nuance beyond which there's no reason to go because you've got everything? How rich do these things want to get? I guess we don't know until we start to sample.
There's always this analogy, right? Peeling the onion. You think, just if I could only have 1 megahertz, right? Or whatever, but no, then that's not enough or whatever. Pick the amount of storage. And so there's always more things that you can do with a more capability. That's, I think, how this town was built on the hardware side with Moore's Law and everybody, just more megahertz and more storage and so forth. And we'll figure out what to do with it. But it's possible that, mystery is good, but, that's what science is trying to do, is find out the unknown through successive approximation. And so we're all interested in figuring it out and understanding more.
So you've been in the thick for 30 years of the advance of all these technologies and all of these applications and so on. And as you're advancing this one, those will be moving along too. And how do you see sort of since you were looking ahead on what this particular technology has in the way of a short, a long, and a very long-term future, how about the whole array of things that it is part of that is drawing on the trillion-dollar industry and so on, which itself is having all these other applications? What's the range of applications that is emerging with this as part of it?
The range of applications of just in consumer electronics, I mean, it's become a monoculture. Really, like in 2008, the sky fell. I was living in Asia at the time, and, the companies I worked with that were living at -30, -40% margin. I don't know if people remember that. I do really viscerally. It was very hard. I had taken millions of dollars from my friends to start a company. I had left MIT. Every day I woke up thinking, I left MIT to do this. It was very hard. But what happened is one company executed very well, Apple, with its breakthrough product, the iPhone, followed by that iPad, and everyone else became fast follower. 10 years later, there's no real differentiation. Everybody's got their candy bar phone. People aren't replacing it. And so what's next in consumer electronics is a good question. So there's been all this money spent on VR and AR. It's not succeeding for lack of investment. That's for sure. I mean, how many $1 billion? It's a lot. I have some stronger opinions, maybe privately I could share, but as a former Facebook and Google executive, I'm required to, no, I'm just not going to go there. So we could do much better, but aren't there more interesting things we can think of to do with technology? And aren't they, right, like how do we fix up the fake news and this sort of weaponization of social media, if you will, is one thing, but that's not long term. Long term is, I think we both saw this quote from Joey this weekend. He's like, will we think of humanity in the future like mankind now, like totally discriminatory because there are all these other living things, and why are we so focused on the humans, for God's sake? There's all of these other things that are living, and don't they have rights? And I know I did that as I took the pig brain yesterday. But they throw away the head. They kill the pig but like, are we going to, these are the sort of the questions of how we deal with living rights and the environment, and can we get to the distant planets, and what are we going to learn and understand and grow, and all why live, right? To learn and have interesting, exciting things to do. But what are those? We think this is part of it, to be able to see inside of your body and brain at 1,000 times cheaper, 1 billion times smaller, and 1 billion times higher resolution. And because there's so many zeros there, we don't even have a business model yet, which gives us a lot of room. People are just happy for us to focus on the white hot risk of just making the thing. And there's a lot of use for it. But I've sideswept your question. What is the answer? You're a big thinker. What is?
Well, it probably relates to my next question, which is, you're an electrical engineer, you've been dealing with hardware and the software that drives the hardware for a long time. Now suddenly you're in meatware. You're doing biology. Pretty thick. Now that's most of the people I know from the so-called hard sciences find it's a real jump to get into the biological sciences because it's such a different world. It's a messy world. It's an evolved world. It's not an engineered world. It seems to consist entirely of special cases. And you can't, all this business of reverse engineering the brain, it was never engineered, so there's no reverse gear for that. What's that like for you to jump into that mud patch?
Well, that happened to me in 1995 when I got a brain tumor. So I unwittingly, as a means of self-preservation, learned all I could about neuroscience and neuroendocrinology just to survive. As I mentioned, I take a dozen medications every day since September 1995. Chemicals that I take, and I've sort of perfected that. Took like 4 or 5 years. And I literally went around the world every 3 weeks for like 6 years, and I could function really well. Just fast forward, that's the thing that makes your hormones. Neurotransmitters are a subclass of hormones. Action at a distance, you make like a dozen in your pituitary gland to the thousands in your body. And sort of learning about how to hack those was pretty fascinating, and how illegal it was to do at the time, because even though I was missing my pituitary gland in 1995, it was illegal for me to replace the chemicals that my pituitary gland used to make just in age and sex appropriate doses, which I couldn't compete in the Olympics or whatever, but when we start to sort of zap neurons, we need to do clinical trials. And so that's a longer frame for when we can ship something.
We're going to go back here just a touch.
Against how we hack ourselves for that, which is great. But I'm kind of cheating, and maybe.
Yeah, I can see self-hacking has got whole new dimensions opening up here. Kind of an interestingly specific question from Claiborne Deming says, I suffer from tinnitus. I once had it.
Suffer from what?
Tinnitus. In the ears.
It's awful.
Could you locate the source of the noise in my brain and shut it down, please?
Maybe we could zap
because it's famously incurable. You got tinnitus.
Famously,
just
suicide rates are much higher because it just drives you crazy over time. I mean, the insidiousness of it. So maybe a friend of mine asked me if we could do that, and we're looking into it because it looks like we can read and write neurons. Can we pick out the right? But that's FDA longer. So imaging is one. When we start to sort of zap neurons, we need to do clinical trials. And so that's a longer frame for when we can ship something safely.
For sure, yeah. Phases,
but we seem...
So, in a nutshell, we are coming down to the last 10 minutes. This is a different approach to Elon Musk's Neuralink. His version, chop a hole in your head, use a robot to implant electrodes strategically throughout different centers of your brain. Use the chipset and the hermetically sealed disc to replace the hole that they cut in your skull so that you have a sealed head again, and then Bluetooth signals into and out of your brain. This lady has been talking about creating wearables that utilize directed energy to read and write information into and out of your brain, as well as image down to a sub-micron level, for those of you that are just joining. So I encourage you to watch this, and I encourage you to research Mary Lou Jepsen, because she has had the inside track to the development of displays and optics and all of the associated physics that are related to waves and photons, which is how microwaves and millimeter waves work. Photons, they're just a different part of the electromagnetic spectrum. And so she says a lot without saying much beyond, or outside of her non-disclosures that she's required to have because she was an executive at Google and Facebook and an MIT professor and graduate, PhD, holds over 250 patents for various components that are found in everyday devices that we all use.
To have the tools in the toolbox, and so putting that in the form of a product we can do. We're interested in getting something that's safe out there for triage and ambulance and urgent care as fast as we can, safely, so that we can build up the volume and then look at these.
So beyond brain things, which we've mostly focused on, is where telepathy happens in cancer, because of the questions of tumors and the blood flow and all that sort of thing. In other aspects of the body with this kind of visibility, what are other aspects beside cancer of the body that might become of interest? This is something athletes will be able to tune up what they do.
Sure. Internal bleeding, like, is your diet changing your the deposits in your arteries, arteriosclerosis? Things with pregnancy, like the placenta is really an organ that grows when you're pregnant, and there's a lot of blood issues with pregnancy, and we're really good at seeing blood. There's also photodynamic therapy, where we can, I didn't show it, but we can also focus the light back down, not just the sound, and that's the hottest area in biophotonics right now.
Photodynamic therapy.
Yeah, we're mostly cut and deliver light, but if you deliver light to like a liver cancer or pancreatic cancer patient, you can lower the chemo doses by 25-fold by adding light. And also there's this saying that sunlight is the best disinfectant, but it's literally true. It's an antibiotic, and you can kill any kind of what is that thing when you're like get the flu and influenza? You can kill it, not the flu. Sorry, I'm just trying to think of.
Can you affect
bacterial
inflammation directly?
Pardon?
Inflammation directly? Could you infect? Well, you're talking about you could go after infection, not just on the surface, but deep inside. Sounds like.
Yes, non-invasively too. So right now, what's being done with photodynamic therapy is bringing in, a fiber optic, cutting a slit and moving it around in your liver, or your wherever inner organs, and then you can reduce these chemo doses or kill different bacteria without the antibiotics, especially antibiotic resistant. And so we could do that non-invasively by basically computing the inverse of the hologram, putting it on a liquid crystal display and illuminating the light to focus it back down. And we've done that in our lab with these phantom tissues and the meat that we've developed, and it does work. And we've built the rudimentary parts of a new LCD, a liquid crystal display that enables us to do that.
Okay, well, she's just alluding to the idea that your phone can be used for long-term therapy to reduce the amount of toxic chemicals used in cancer treatment. That's just one example. And this idea of being able to use something like your phone or a wearable to treat bacterial and potentially viral infections. Energy-based medicine. And that is the level of sophistication by which our modern devices are produced. So these are powerful sensor platforms that we all have and that we all covet more than our wallets.
But since we have the focused ultrasound already, we're just trying to figure out what do we do to put together kind of a first rudimentary kit rather than what we can do. But the key thing is nothing in medical imaging and very few things in hospitals are made in the consumer electronics manufacturing infrastructure that's a monoculture from the smartphones and the recovery of the economic crisis. Healthcare has gotten super expensive. How do we democratize healthcare? There's not enough doctors in 3 continents in the world.
All right, blah, 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 blah. I want to show you something else. We got a few minutes left. And it's this, the thermoacoustic effect, whereby ultrasound can be made using your own tissues with radio waves, electromagnetic waves. So here you go.
Okay, so let's talk a little bit more about the specifics of what we are proposing here. So our fingerprint reader relies on the thermoacoustic effect, and the thermoacoustic effect is essentially that we expose the tissue with microwave or optical excitation that generates small thermal expansions that give off ultrasonic waves. We intercept the ultrasonic waves and sort of reconstruct an image based on that. So with this method, we use a combination of microwaves and ultrasound. The microwave gives you contrast information, spectral information, and ultrasound gives you structural and resolution. So the combination of the two sort of gives you enough of the features that you need to reconstruct the blood vessel library that generates these low false alarm rate detections.
Okay, microwave radiation can generate ultrasound and can also be used for its own imaging properties. So the ultrasound can be generated with microwave radiation, and then the very same device can then read the movements that it created. So enjoy your ultra wideband, enjoy your new fancy phones, enjoy the fact that you're being imaged and potentially modulated with ultrasound with things like microwaves. It's a very real thing. Photoacoustics is another one that's done with light. And we're talking about temperature rises, right? You see the temperature rise here, 0.001 degrees Celsius, in order to get some type of a measurable effect. In this case, it's for imaging, for biometric authentication. Thermoacoustics are very, very possible with existing wireless systems. And we are not in Kansas anymore. We are now bridging these systems with light-based systems and with sound-based systems in compact, sleek, sexy devices known as 5G, ultra-wideband, model number, blah, 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 blah. Go ahead and go look at the new phones out there. They all advertise the same general kind of way. What WB, UWB, 5G, whatever. And it is this new class of device that is a giant leap as it relates to the sensor platform that you're putting in your pocket, which is also a directed energy-based system. I will leave the term weapon out of it. It is a directed energy-based system, as much as it is a tracking device. Let's see what else this has to say.
Now, potential for thermoacoustic imaging. One thing we have to emphasize that the temperature rise we discussed is only in the millikelvin regime. We're not talking about large temperature rises. These are instantaneous, very low temperature rises. And we also have a reasonably high contrast and resolution for 3D imaging. Now,
high contrast resolution with 3D imaging. So this is a document, ultra wideband imaging. Ultra wideband radar in medicine, very real thing, very, very real thing. They're able to track heartbeats. They can image and understand skin, fat, muscle, cartilage, bone with a pulse of energy. Ultra wideband pulse echo delay. This is the 3D modeling, 3D imaging with electromagnetic energy. This is in addition to being able to generate ultrasound with a thermoacoustic effect using the same exact thing known as ultra wideband. And it can image very, very well. No other direct comparison is made. Here it is right here. Functional magnetic resonance imaging is actually providing images of moving internal organs, but as its uses induce field, the patient has to be confined into space. Ultra wideband radar using a radiated field lets the patient be absolutely free in space. So it is imaging like a functional magnetic resonance imager, only you are able to move about freely. It also says that this thing can be used here. It can simultaneously track mommy's heart. It can understand the placenta. It can understand infant's heart and movements and subsets therein with ultra wideband radar. This is in your phone today, folks. And it also says here, it is well known the skull and the brain are somewhat transparent to infrared energy. Infrared transmission spectra of the whole brain are being used to investigate brain metabolism and blood circulation. That's the measuring the blood flow thing we were listening to earlier, especially in newborns. Using ultra-wideband radar-based systems, the same studies can be performed. Oh, ultra-wideband systems can then read blood flow and blood circulation, all that stuff, huh? Interesting. Can also be performed with a time-resolved technique, enabling IR imaging of sectors of the brain in the body and non-invasively with better results. Of particular interest would be the estimation of hemoglobin oxygen saturation in selected brain areas. The ultra-wideband radar adapted, otherwise well-known method of oxygen saturation monitoring could be used. So the very same things that lady was talking about doing with light can be done with ultra-wideband, and that is in your phones today. Good night.